So today's topic is ionization enthalpy. Actually, it is a quantitative measure of the tendency of an element to lose electron. How easily a species can release electron. So that measurement can be done in the form of ionization enthalpy. What is ionization enthalpy? So it is the amount of energy required to remove an electron from an isolated gaseous atom in its ground state. Here we are assuming X as an atom. What will happen? X in its gaseous form will liberate one electron or release one electron. For removal of that electron, we have to provide energy. That is called as ionization enthalpy. For example, in this figure, this valence shell electron is given of that X atom. So now energy is provided. So once that energy is greater than the force which is exerted by the nucleus on this electron, or the force by which this electron is held by the nucleus, once that energy provided externally, it exceeds. So this electron is removed. What happens to this? Now there will be two shells. This outermost shell will be removed. As a result, this will be converted into ion. Now you can see that there are 2 and 8 electrons in the shell, and it acquires a positive charge. That released electron plus 1 electron is released. So X positive ion is formed. So for this process, some energy is required, and that is called as ionization enthalpy, mentioned by delta IH. Since energy is required, so ionization enthalpy is always positive. Okay. In this case, this is first ionization enthalpy. In the same manner, the next electron can be removed. So again, energy has to be provided, plus 1 electron. So this X positive is converted into X2 positive. This process is taking place in gaseous state, and 1 electron is released. This will be called as second ionization enthalpy. Okay. Next are successive ionization enthalpies. Successive ionization enthalpy term refers to the amount of energy required to remove electrons one after another from the same atom in gaseous state. So those energies, whatever energy will be required for this process to take out electrons one after another from the same, is called as successive ionization enthalpy. For example, again, if we assume that same atom X in gaseous state, it will be converted into X positive plus 1 electron. That means 1 electron has been removed now. This will be called as first ionization enthalpy, represented as delta. Delta means change, H means enthalpy, and I stands for ionization. Since 1 electron is removed, so it will be first ionization enthalpy, right? Now this X positive, which is formed in the first step, that is removal of first electron, now again in the gaseous state, when another electron is removed. So when another electron is removed from this X positive, it will become X2 positive. The charge will increase, positive charge is increasing continuously as the electrons are removed, and one more electron is removed, is lost by this species. So we will get X2 positive. So it will be called as second ionization enthalpy, and it will be represented by delta IH2. Okay. So these are called as delta H1 and delta H2. These will be called as successive ionization enthalpies. Their magnitude will vary. Now in this figure, first ionization enthalpy, that is, if we assume that in this case there are 13 electrons, 2 in the inner shell, 8 in the next shell, and 3 electrons. Now because this is X positive, so there will be only 2 electrons. The third electron is already removed, so it is X positive, and it has now how many electrons? 12 electrons, and 2 in the valence shell, right? So it has already acquired positive charge due to loss of this electron. So first ionization enthalpy for this change, whatever energy is required, that was first ionization. I hope you are getting this. Then this X positive is changed once one more electron, that is this electron, is removed. So if this electron is removed, what will happen? It will carry one positive charge, that is 2 positive. Now one positive was already there, now another electron is removed and electron is negatively charged, so it will release that electron and it will acquire positive charge. Now as you can see in this valence shell, this electron is removed now and we have only one electron. So whatever transition or whatever energy is required, that is second ionization enthalpy. Okay. Now for the third, if that last electron, now if this electron is also removed, what will happen? Now all the 3 valence shell electrons, they are removed and this shell is lost now, and we have 8 electrons in the inner shell, and the species has acquired 3 positive charge. That means how many electrons are removed? 1, 2 and 3. So the energy is required for this process one after another, because from the same species we have removed 3 electrons, so energy required will be called as successive ionization enthalpy. If we relate the successive ionization enthalpies, for example, this is X atom or atom in its ground state. In gaseous form, there were 3 valence shell electrons. Now it is converted into X positive by loss of 1 electron. Now what will happen to the size of these two? So once there is formation of this unipositive ion, the change takes place in terms of their protons and electrons. So in the ground state or in neutral state, the atom has 13 electrons and 13 protons as well as 13 electrons within. But in this univalent or unipositive ion, 1 electron is released. As a result, there will be 13 protons and 12 electrons. As we know that nucleus, it always attracts electron, because nucleus carries net positive charge and electrons, they have negative charge. So there is always a force of attraction that we call as nuclear charge or effective nuclear charge. So now out of these two, which one will have greater effective nuclear charge? It's obvious that 13 protons, they will attract 12 electrons with greater force. Hence, effective nuclear charge in unipositive ion will be greater than that of its atom. Now in the same manner, for second, when there is bivalent ion formation or X2 positive ion is there, that means 2 electrons are removed. So again, the nuclear charge or effective nuclear charge, that tends to increase. So therefore we can say that as the electrons are removed one after another, the nuclear charge goes on increasing. Once the nuclear charge increases, so it results in decreased atomic or ionic radii, or size decreases. This we have already discussed, that the size of the cation is always smaller than its parent. So the same thing takes place. Okay. So the first ionization enthalpy and second ionization enthalpy, if we compare these two, so second ionization enthalpy value will be greater than first ionization enthalpy. The reason is quite clear now, right? Because after removal of electron, an effective nuclear charge, that increases, and hence greater the nuclear charge, so size will be less. But now another electron, when it has to be removed, so then it will require more energy. Okay. Some interesting trends about ionization enthalpies. The first ionization enthalpies of elements having atomic number up to 60 are shown in the graph. And the periodicity of the graph is quite striking. In this graph, it is found that the maxima or the maximum value of ionization, it was found towards right side of the periodic table, that is towards noble gases. For example, helium, it has maximum value, then neon, argon, krypton and xenon. They are having maximum values, as you can see. Whereas the minimum value, they are found towards left side of the periodic table, that is alkali metals, lithium, sodium, potassium, rubidium and cesium. Okay. Now variation of ionization enthalpies across the period. So we will analyze now, after going through the basic term, what is ionization enthalpy, what are successive ionization enthalpies. Now we will relate that how these ionization enthalpy value that varies when we move across the period as well as we move down the group. So variation in the periodic table, variation of ionization enthalpy in the periodic table. As we can see that from moving left to right, this is second period, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. These are second period elements. So second period elements, when we have analyzed them for ionization enthalpy, it was found that ionization enthalpy value, it goes on increasing across the period. The reason is quite simple. When we move across the period or along the period, the electrons, they enter in the same shell. We have already discussed in atomic radii that addition of electron that takes place within same shell, and hence if the electron number increases within the same shell, what happens? Nuclear charge tends to increase. Effective nuclear charge that we call. And once that effective nuclear charge increases, so it will result in decreased size. And due to decrease in size, the removal of this valence shell electron, for example from neon, or we can say from fluorine, it will become difficult. In case we are to remove, so we have to provide large amount of energy. Hence, ionization enthalpy will be maximum when we move across the period. Now the same variation can be, we can analyze the same variation by or through this graphical representation. Again, it's represented for the same period, that is second period. Lithium, vertically ionization energies are plotted and horizontally nuclear charge. So nuclear charge goes on increasing, that's why. But what happens to ionization enthalpy? Ionization enthalpy value also goes on increasing, right? So lithium has least ionization enthalpy, whereas your neon, it will have maximum ionization enthalpy. Okay. But in between, there are certain abnormalities. Beryllium has greater ionization enthalpy, but as we move from beryllium to boron, the nuclear charge increases, so therefore boron should have higher ionization enthalpy. So this is abnormal behavior. And in the same manner from nitrogen and then oxygen should have higher ionization enthalpy, but it has lower ionization enthalpy. But in general, ionization enthalpy value goes on increasing. Nitrogen, as we can see in this, for beryllium, 2s subshell is filled. For nitrogen, half filled 2p subshell is there, and for neon, fully filled subshell is there. Now, how to explain that anomalous behavior? First of all, from lithium to beryllium, there is increase in ionization enthalpy. It's obvious because nuclear charge tends to increase. Now from beryllium to boron, there is decrease. Beryllium has 899 kilojoule per mole energy. We are talking about first ionization enthalpy. Okay, and then for boron it's 801 kilojoule per mole. which is lesser, and it should be more. So the reason is the electronic configuration. So on the basis of electronic configuration, we can explain this anomalous behavior. Now analyze the electronic configuration of beryllium. Beryllium has 4 electrons. As a result, it will have 2s2, 1s2 and 2s2 electronic configuration. So the electron now has to be removed from fully filled 2s subshell. In fully filled subshell, it has greater stability, hence we have to provide more energy. But if we relate it with boron, why boron has lower ionization enthalpy? So we can see it has 5 electrons, Z equals to 5. There will be 2 electrons in 1s, 2 electrons in 2s, and the 5th electron is in p, that is 2p1. So there is 1 electron in boron and p subshell is partially filled. Either it is half filled nor it is fully filled. So this electron can be easily removed. Whereas in previous case, due to greater stability, the removal of electron was difficult. Hence, boron has less ionization enthalpy because we can take out this electron easily. So unpaired outermost electron is there, whereas completely filled 2s orbital is there in beryllium. Hence beryllium has greater ionization enthalpy, whereas boron has lower ionization enthalpy, although boron has greater nuclear charge. Is it clear? So this is one of the factors. Only just we can say that only just it's not the size or nuclear charge, but there are some other factors, and out of those, one factor is electronic configuration. The species which will have stable electronic configuration, that will have higher ionization enthalpy. Variation of ionization enthalpy down the group. Ionization enthalpy, it goes on decreasing as we move down the group, because the outermost electron goes away from the nucleus. So due to this, there is an increased shielding effect of the nuclear charge by the electrons in the inner layers. Okay. So due to that increased nuclear charge, the valence shell electron is not attracted as strongly, and we can say that shielding effect outweighs the nuclear charge, increased nuclear charge, and hence the removal of electron becomes easier as we move down the group. So conclusion is that the value of ionization enthalpy that goes on decreasing down the group. IE value decreases as we descend the group. Reason being due to increased size. Or we can say that the inner electrons, they tends to repel the outermost electron, hence shielding effect is more, which results decreased nuclear, which results in easier removal of electron. Okay. So lithium will require highest energy ionization enthalpy, whereas francium will require lowest. Reason being the bigger size or that increased shielding effect dominates over the nuclear charge. Okay. Now towards end, the factors affecting ionization enthalpy. So we have discussed what is ionization enthalpy, how it varies in the period, how it varies down the group. Now what are the various factors which can affect? Although we have gone through each one of them, just a quick recapitulation. First one is size of the atom. So can we conclude how ionization enthalpy will vary with size? So greater the size, smaller will be the ionization enthalpy. So with size, ionization enthalpy, what's the relation? It is the size, smaller will be the ionization enthalpy. Then second factor we have discussed, that is electronic configuration. So electronic configuration, if stable the electronic configuration, and stable electronic configuration is the case of when the shells are fully filled or half filled. So stable electronic configuration means more ionization enthalpy. Okay. Then charge on atom. So charge on atom means whether it will be positively charged, right? So charge on the atom, greater the charge, the removal of electron will be difficult. Because, for example, Mg positive is there. We have removed one electron, and then another species is Mg2 positive. Now, out of these two, from which species the removal of electron is easy? So Mg positive has changed to Mg2 positive, so size of Mg2 positive is smaller, and smaller size means greater nuclear charge. So greater nuclear charge means more ionization. Okay, so greater the charge on the atom, so greater will be ionization. Then shielding effect or screening effect. So greater the screening or shielding effect, lesser will be ionization. Ionization enthalpy will be required less. Ionization enthalpy. And then the last term is penetration effect. Penetration effect is related with S block, P block, S subshell, P subshell, D subshell, and F subshell, as how they are arranged. So S will always lie to the inner side, or it will be nearer to nucleus. So the penetration of S is maximum because the electrons of S are strongly attracted by the nucleus. So hence we can relate it that S has greatest penetration effect, so the ionization enthalpy for removal of electron from S subshell will be highest. So removal of electron will be difficult from S. So these are the